have an administrative question. How do I schedule a proctored test?
Uh, you probably saw the email already. One way you could just
Yeah.
show up at one of my classes, but normally what you do is you call the testing center at the class at the campus that's closest to you or the one that you find most convenient to go to, and you can either email them at testing center or you can call them on the phone. Either way, you can find their email address and their phone number on TCC's website. And you just
Okay.
call them and tell them I've just submitted the order, so everybody at all the testing centers should know about my test. They have the password, they have everything they need, they know what you're supposed to have. They can tell you whether you need appointment. You do normally have to bring a photo ID, but other than that, I'm not sure what the rules are. I know one rule was that if they close at like 7 and you have a test that's supposed to be 2 hours, then you can't start it any later than like 4:30 or something like that. But that's about the only real major rules. And each campus has a certain night that their testing center is open at night so that we have at least one testing center open for each campus at some time in the night during the week. So if you need to do
Okay.
it on a night, it might be one specific campus that's not the closest one to you.
Okay. Yep. Sounds good. Sounds
And
easy
it's all
enough.
free that way. There's other services you can pay for, but unless you're interested in possibly paying, or if you're so far away that you couldn't come to our campus, that might be a worthwhile choice.
Okay. Well, yeah, I'm not too far from the Virginia Beach
Oh,
campus,
okay,
so
good deal.
yeah, that'll work.
All
I
right.
did have a question about the one of the lectures from last week. I think what I'm going to do is kind of maybe I need to gather some thoughts on it. It was about the trig substitution,
Okay.
one of the trig substitutions.
hmm
Um,
In that
that I
integral problem we did
in
last time,
the
probably.
yeah, exactly in the integral problem, and I wasn't tracking where how that substitution was made. And
Gotcha.
admittedly, it's been a minute for me since I looked at integrals and trig and anything to do with math. So
Yeah, no
um,
problem. Actually, I can go ahead and give you a little bit of help on that while we're waiting. Anyways, it's a common that's a common problem that students have in general, but it is also a common thing that we sort of as teachers are get excited about because it's the one integral we can actually do. There's not very many in real life that we can actually solve, so we've got basically the 4 or 5 problems I work for you, and everything else you have to write code to do. So
yeah,
not necessarily
okay,
fun, or
yeah,
use Mathematica or something.
yeah, good deal, good deal. And as we're talking here, I'm trying to find in my notes where it was, but at any rate, it was from last Thursday on the
hmm
first integral problem.
Yeah, I figured it was that one. That's what I'm pulling up right now.
Okay. And
So
I wish I was a little more organized here with my question because I don't really have it a
Oh, it's
tight
very
question for you as
exciting for
yet.
me. I'm really happy that I'm for once the most prepared person. So, yay for me. I'm assuming
Yeah,
you're talking about this substitution right here.
actually, I pulled it out of my notebook, so I do have it in front of me.
Yeah. So, what I remember is when we have the plus in here, then we generally use 1 plus tangent squared from the trig identity 1 plus tangent squared equals secant squared. So the big problem
Okay.
here is the variable that we're integrating with respect to is dz. So that's the part that's the problem. You could, in principle, call this whole thing down here u, but you would need a z up here, and we don't have that. This one, you actually do have a z up there, so that technique of letting r squared plus z squared equal u, that would work fine for working this integral. But in this case, since we don't have a z up top, we needed to do something different. And the thing that we use is the trig substitution. Let z, in other words, replace the z with that number times tangent theta. Because if this is squared just like the r is squared, so if you let z equal r tangent theta, then it becomes r squared plus r squared tangent theta, which means you can factor out that r squared like I did here. And that leaves you with just the 1 plus tangent squared. And the trig identity says that 1 plus tangent squared is secant squared. So you end up getting secant squared raised to the 3 halves power. The 2 cancels out with the squared on the secant, and you end up left with just secant cubed in the bottom. And you had from the substitution, since we found that dz was r secant squared theta d theta, we could automatically replace this dz with r secant squared theta d theta. So we had a secant squared on top and a secant cubed on the bottom, which left just a secant in the bottom, but a secant in the bottom is the same thing as a cosine up top.
Okay. Yeah.
So that's a lot of words, but that's
Yeah.
that's the crux of it. Was there anything specifically that bothered you about it?
No, I think everything you just said is going
Yeah,
to answer
and
my
the good
question.
news is this. For instance, I told you last time that this is the second hardest problem you'll do this whole semester, and
Yeah.
that's right unless we get to quantum mechanics. There might be some stuff that might be a little bit harder, but not mathematically harder, just weirder. Uh,
Okay.
the other thing that is the hardest, it, oddly enough, involves the exact same integral with the exact same trig substitution.
Oh, nice.
So you'll
Okay.
see this like three times throughout the course if you took the two semester sequence.
Oh, sweet.
So
All
you will
right.
get plenty of time to use it. And yeah, let me know. What I told my students to do is try to work the same problem over again. You can do it
Mhm.
instead of thinking about going from infinity to infinity like I have here. You could actually go from negative L over 2 to L over 2 instead. And then, in fact, there's an online extra credit problem that you could do doing that, where you'll get a different formula for it being a finite length of wire, whose length is L, and you can actually compare the results from the one whose length is L and from the one whose length is considered to be infinite, and find out how close those two are. For instance, I made the argument that if r is like 10 centimeters, then as long as the length of this is about 20 excuse me, length of this is about 200 centimeters, then it should be fine, because 10 times 10 is 200, or excuse me, 10 times 20 is 200. So
Okay.
normally it's a factor of 10, or in this case it was a factor of 10 times 2, which you really didn't need the 2, but you did to make it in the center. So there's a neat little
Okay.
problem on that you can try if you like, and it gives you more practice just doing the same integral over and over again.
Okay.
All
Sounds
right,
good.
no
Yep.
problem. That's a good question, and like I said, that is the number one question that people have. They often get shocked by some of the calculus, especially if, like you, I think you said you were mentioning that you hadn't had calculus for some time. So yeah, those were the most difficult techniques within the whole course. So they're
Okay.
definitely the ones that go first.
All right. That's good. That's good.
All right.
Well, thanks for that.
No problem. And like I said, text me, email me, or whatever if you have any other problems. That'll be fine. Or if you just need other explanations of it.
Yeah, we'll do.
Cool. Well, we've went to 26 after, so that's well after the time that class is supposed to be meeting. So I'm going to go ahead and get prepared to start this next chapter. Well, actually, let me start off with the end of last chapter. I've essentially finished chapter 21, but in so doing last time, I quickly jotted down two results that you'd need, but I didn't really give you any examples of it, and I didn't really derive it. So I'm going to sort of do that first to give you a better understanding of where those two formulas came from and what a dipole is. So I'm going to start with that, and then I'm going to go to chapter 22. So I'm going to go ahead and share my screen again. And there it is. Should be popping up any minute now. So what I wanted to express to you is that a electric dipole, which is what we're dealing with right now, electric dipole. It's basically an idea that you can imagine a single charge separated from another identical but oppositely charged particle. And actually, let me use my fancy drawing techniques. I'm going to do that, and I'm going to do this. And what we're going to have here is, let's say this guy is the positive charge and this guy is the negative charge. And they both have a charge of, say, Q. So this one would be positive Q and this one would be negative q. And specifically, these are point particles, is what we're imagining. And the distance between the point particles is going to be called a distance d. And in fact, we can even define a vector d, and I'm going to use that. Okay. The weird thing is we are going to define a vector, and the vector we're going to define starts, you can imagine it starting in the middle of the negative charge and going to the center of the positive charge like this. And the reason why I point that out is I want you to recognize it's exactly the opposite direction of the electric field that's created by that positive and negative charge. Because obviously, hopefully you recall that when I said, when I defined an electric field, we specifically define the direction of the electric field as the direction that a positive test charge would be compelled to move if it was at that particular location in the field. So, for instance, if I put a positive test charge, let's say right here in the center, if that was a positive charge, it would be compelled to move towards the negative. So this vector here that I just drew in red is a way of expressing my vector that I call d. So we'll call this vector d like that. And then there is a electric dipole or electric dipole moment, and I'll say, well, actually, I'll say moment because we sort of use the phrases interchangeably. We'll say electric dipole or we'll say electric dipole moment. And the big deal is that the formula for it is P is equal to the magnitude of the charge, Q, times the vector D that I just defined. So if you define that as the dipole moment, then we can get sort of neat stuff. So just remember that's really what it's supposed to be. This, I'll redraw these since I had to cover up the plus sign with the red vector. I redrew the signs of the charges just to make sure you could still see them, and I do the same thing with the circles. So that's what the electric dipole means. Now, for instance, this is what we treat, for instance, a water molecule like if you're doing, for instance, taking an MRI of a human or whatever, the water molecule acts like an electric dipole. If you remember from your chemistry that hopefully you had, but if you haven't had any, I'll explain a little bit now. But we sort of picture a water molecule as like a Mickey Mouse head. So, Mickey Mouse has this big head and then he has this big ear over here and an ear over here. Those two ears are markedly smaller than his head, and they're supposed to represent the hydrogen atoms. And the bigger one, that's the size of his head, is supposed to represent the oxygen atom. Well, if you look in a periodic table, the oxygen is just two to the left of neon. Yeah, I'm pretty sure it's neon. Neon, which is a noble gas. So when you actually fill the outermost shell of oxygen with the two donated electrons from the hydrogen, that makes a complete outer shell. And in fact, that oxygen has a larger electron affinity for those two electrons than the hydrogen does. So you can sort of think of this Mickey Mouse head as if the oxygen is winning the battle of the negative. So you can place a little negative charge right by the chin of Mickey Mouse's head, and then right at the top, right between his ears, that would be the positive sign. And then you just forget about the existence of, atom, atom, atom. You're just thinking of it like this as an electric dipole. And when that flips from pointing, say, this way to that way, that's a very specific amount of energy that's changing from it being in a magnetic or electric field or whatever. So when it flips like that, it has a characteristic energy that it gives off. And that characteristic energy has a characteristic either wavelength or frequency. So one of the things you can get from an MRI, in addition to the cool pictures, is a graph of energy versus wavelength or energy versus frequency. And you can look up various spikes in the MRI portion, and those spikes correspond to different elements and different compounds and things like that, are, for instance, water molecules. Uh, Aluminum, for instance, has one of those type spikes that appear, and that was, for instance, one of the things that we first learned about Alzheimer's when we first started noticing this early onset dementia in the 80s. So
Is
my
that
grand,
why you
go ahead.
can't drink fluids? prior to an MRI?
There shouldn't be any
Or
problem with that. But if you
I
were
do know.
looking
Oh,
for
wait,
your
never mind.
stomach, it would cause
Yeah.
problems. Yeah. So, I would say probably not the most pressing reason, but it would certainly give you a different, result than you'd expect. Like, you would obviously see, well, this person drank something that's mostly water, so there's a ton of water in there, and your graph would come out differently. But I don't think it has anything to do specifically with like, causing adverse reactions to the patient. But the big thing was like in the 80s when they did that with the MRI, we reported for a brief period. I say we scientists and the news reported that they were finding aluminum spikes in the brains of patients with Alzheimer's. So I remember a lot of people talking about, okay, well we should stop, using aluminum to make our canned drinks. We should stop using aluminum cookware. We should stop storing things in aluminum cans and all that stuff. Well, I think the latest word is that I think Alzheimer's turns out to be one of these prion type disease, not unlike the I forget that fancy name for it, but basically mad cow disease, Jakob something disease. Those are what we call prion diseases, and they tend to, again, this is not my field, but from what I read, it seemed like that prion disease has a tendency to make certain metals appear in in various organs, and therefore the thing that actually caused the Alzheimer's also caused the aluminum spikes, not that the aluminum spikes cause the Alzheimer. So we've given up that. That's why we're still drinking drinks out of aluminum cans and still cooking with aluminum cookware. But like I said, just having that knowledge that a water molecule behaves like an electric dipole, then we can immediately look for the ramifications of that dipole. And what are those ramifications? Well, that's what I'm getting ready to show you now. So imagine for a second if we had electric fields. I'm going to draw these electric fields as pointing to the right. So here's an electric field. It's going to be fairly uniform electric field, and it points perfectly horizontally to the right. And it's basically the same strength everywhere. That's what I was meaning by saying it was uniform. And then what I'm going to do is I'm going to imagine a dipole having a positive charge here and having a negative charge here. And therefore, the electric dipole would be a vector that points from here to here. Okay, so you might think, well, what exactly is the effect on this dipole being in this electric field? Well, we can say, for instance, that this point dead center is going to be the pivot point. So we're imagining that this dipole sort of has an axle right through the middle of it. And we're going to call the point where that axle hits the vector the pivot point. So we can picture that obviously this electric field, which remember the electric field points in the direction a positive charge tends to move, that would tell you that this positive charge is probably going to try to move this way. And that would also tell you that this negative charge should move the opposite direction like that. What that means is both the positive charge at the top and the negative charge at the bottom are compelling this dipole to rotate from being at that diagonal angle to rotating clockwise. So what we're going to do is calculate that torque. You might recall that torque is equal to R cross F. That's one way of calculating it. Another way we calculated was we took the magnitude of it, which we could write as T or tau, excuse me, with a vector symbol with absolute value bars around it, or we could just write it without the vector symbol. And in that case, it became R times F times the sine of theta, which could also be interpreted as R, the component of R that's perpendicular to F, or you could say it's F, the component of F perpendicular to R. So it could be either one of those. I'm going to make use of that now. And what I'm going to do is assume that this clockwise rotation is a positive torque. So I only want to calculate it, and I'm not worried about the sign being weird or anything like that. So we can imagine, for instance, the torque on the positive charge as being clockwise. and it's going to be equal to the lever arm, and the lever arm, of course, is half the length of the vector d, so I'm going to say that's d over 2. The force, remember from our definition of how we actually define the electric field, the force is equal to q times e, and the charge we have is plus q, so I'm just going to write q times e for the force. Now that gives me the lever arm, the d over 2, times the force. And what we need to do now is remember that we're taking a cross product, so we really have to pick the component of either the lever arm that's perpendicular to the electric field or the part of the actual force that's perpendicular to the lever arm. Well, ideally, what you're looking for is a force that would be perpendicular to the lever arm. So let's imagine for a second that this green vector is really perpendicular to the lever arm. Okay, so if that is in fact perpendicular to the lever arm, that is the component of this little red vector that I drew, this guy right here. That's the component of it that's perpendicular to the electric field, or in when we actually line it up, it'll be actually parallel to the electric field. So right now, that's sort of the maximal torque. So we can imagine this little vector right here being the sum of this green component here plus a green component here. And this is, for instance, the force parallel to the lever arm, which we normally call L or R or whatever, right? And this is the force that's perpendicular to the lever arm. Okay, so that's really what we want. Now, if you assume that this angle right here is theta, then you can see that this angle right here would also be theta. And since this angle, let me use my pointer, since this angle from here to here is 90 degrees, then this one must be 90 minus theta, but this one is going to be theta. So I'm just going to write the angle theta right there and remind us that it works that way. So now, in order for me to take this red vector, which is what the d over 2 times qe gives me, well, at least the QE part gives me, I'm going to take that component by multiplying the magnitude of this hypotenuse, the magnitude of this hypotenuse times the sine of theta. That'll give me that component because it's opposite the angle theta. So I'm going to write this result as d over 2 QE times the sine of theta. Now I'm going to do the same thing for the negative charge, which is also causing a clockwise torque. So, in other words, the fact that I'm using it as a positive or negative doesn't really matter. The main thing to see here is both of these torques are tending to make the same rotation, a clockwise rotation. So we're just going to add them together when we get the result. In the case of the minimum, or excuse me, of the negative charge, the lever arm is still d over 2, because remember that whole red vector has a length d. The force is still q times e, and the direction is pointing to the left now. But again, you can say that that angle is theta, and therefore you could imagine breaking this force vector up into this component. Notice I'm drawing it on a different place than I did last time, but it's still the same vectors, times this one. This is the F perpendicular to L, and this is the F parallel to L. We want the F perpendicular to L because that's the one that gives the max torque, is when you actually have the force exactly perpendicular to the lever arm. So again, to get that component, I multiply the hypotenuse, which is the QE, times the sine of theta. Oops, I should have wrote that in red. So I write it times the sine of theta. So we can now say that torque total, which is just going to be equal to torque. Notice I'm working in magnitudes, not vectors. The torque total will be equal to torque due to the positive particle plus torque due to the negative particle. Luckily, they both cause a clockwise rotation, so we can just add them. If one was clockwise and the other one was counterclockwise, for instance, we'd have to call one negative and the other one positive. But in this case, we can call them both positive. And what we get is d over 2 QE sine theta plus d over 2 QE sine theta. I think you can see that that gives you a result of d QE sine theta. Just combining like terms, we get d times QE times the sine of theta. Well, hopefully that looks enough like what you're used to from our definitions of the torque formula. Namely, torque is equal to R times F times the sine of theta. And what we see is this quantity right here, D times Q, is our electric dipole moment. So this is P, and this is E's magnitude, and therefore this formula is exactly equivalent to saying that torque as a vector quantity is equal to P, the electric dipole moment, crossed with E. So that was the result I gave you at the end of class last time, and it was correct and everything. It just I didn't give you any explanation for it whatsoever, but now we see how that came to be. Now, there is another one I gave you, but that one, if I remember correctly, I think I copied it down and made a little bit of a copy error. Specifically, I left off the negative. So I'm gonna sort of show you that, but I'm really just giving you the result. Uh, what we do for that one is we're trying to calculate, for instance, the work done in, let's say, rotating the magnet or having a hard time saying the word rotate, rotating the electric dipole moment. That requires a certain amount of work. So we can say work, which we remember is equal to the integral of f dot dx or f dot dl, say something like that. That's what we had from last semester. So we could use that, but it turns out that that actually works out to a slightly easier formula where you can use the integral of the torque d theta. And of course, the torque we found was equal to P times E. Remember, P is the Q times D, so we got that. So it's P times E times the sine of theta, d theta. And we're going to imagine that specifically going from, let's say, theta 1 to theta 2. So we're imagining it again sitting in here, and maybe it's tilted at an angle theta 1 with respect to the electric field, and then afterwards it's rotated to a direction theta 2 with respect to the electric field. That gives us basically the integral of sine. We know that the derivative of cosine is negative sine, so the integral of sine must be negative cosine. So what we're going to get is P times E. They were constants that just came out. And now we're going to take, yes, the derivative of sine is cosine. So the integral of cosine is sine. Something like that. Anyways, so we will get, sorry, cosine theta 2 minus cosine theta 1. And that's actually how you go about working out how much work it takes to rotate a dipole moment. Well, it turns out that if you want to use that as a potential energy, remember we learned that the change in potential energy is equal to the negative of the work done by the force. So when you do that, you get U is equal to negative P dot E. And the reason why I used a dot product there is because remember A dot B is equal to the magnitude of A, which is one of the vectors, times the magnitude of B, which is another vector, times the cosine of the angle between them when they're tail to tail. So the fact that I've got P times E times cosine theta tells me that the magnitude is really just P dot E, and the fact that it's the change in potential energy is the negative of the work done is what gives us that negative. So this is the formula I meant to give you last time, but I gave it to you without the negative. Now you have some understanding of why we have that formula at all. The most beautiful part about all this is the whole reason I'm doing this is we'll find out later on that magnetic fields also exist, and that magnetic fields can also be represented not by electric dipoles but by what we call magnetic dipoles. In that case, the magnetic dipole mu is also a vector, only it's a little weird to explain exactly what it is, so I won't try to explain that right now, but we will get to it later. But that letter mu is what we use for it, and guess what? The formula for torque for a magnetic dipole is torque is equal to mu cross B, where B is the magnetic field, just like P cross E, where E is the electric field. Similarly, there's a formula for the magnetic moment, which I'll do this one in red. There's a formula for the potential energy, excuse me, of a magnetic dipole, and that is U. Oops, it turned it into an eraser all of a sudden. That is U is equal to negative mu dot B. That one might also be one without the minus. I can't remember. But the main thing is they look a lot alike. And that's the first thing where you start to understand that what I'm teaching you about Maxwell's equations is that the electric field and the magnetic field, which we've always thought of as two entirely different things. I mean, you never think of magnets in the context of you getting, your finger shocked when you walk up to a doorknob in the wintertime, right? Because electric and magnetism doesn't seem to be that much related. But the more you learn, you find out that really the electric field and the magnetic field are just just different sides of the same coin. So this is the first chance for you to see that lo and behold, the formula works exactly the same way. So let's do an example just to give you an idea of how we go about using this. So I'll call this example one. And what we're doing here is we're going to say that the magnetic moment, or there I go with magnet. See, I brought up magnetism. Now I'm going to say magnetism about 1,000 times instead of electric. So the electric dipole moment for a water molecule, so I'll say P sub H2O, okay, has a magnitude that is equal to 6.1 times 10 to the negative 30th coulombs times meters. Now, notice that is exactly the unit you expect since we defined torque or excuse me, since we defined the electric dipole moment as Q times D. This has units of coulombs and this has units of meters. So the coulomb meter should be the unit for the electric dipole. So that's consistent with that. And we're going to imagine that a water molecule was placed in a uniform electric field. So we're going to say E, might help if I actually write. We're going to say the electric field that the electric dipole is in has a magnitude equal to 2.0 times 10 to the fifth. And again, the units for the electric field are Newton per coulomb. Later, we'll learn that it's volts per meter as well. What we'd like to find out about this is A, what is the maximum torque that can be applied to the water molecule. So that's one question we want to know. Another question is what is the potential energy at when the torque is at its maximum. So what is U for PH2O when torque is a maximum? Okay, so we'll start with that and see what we can come up with. So here's our solution. It's important to remember that when we're working with formulas like torque is equal to P cross E, it's important to remember exactly what the theta is, for instance, in the formula that tells us the magnitude of the torque is P times E times the sine of theta. How does that theta depend on anything? Similarly, what about when you say the potential energy is excuse me, is negative P dot E, which also equals negative P E cosine theta. So it's important for us to really understand what those angles are. So I'm going to try to give you that as an idea. Uh, First off, what we see is for part A, torque is maximum when, so looking at the formula, we got torque equals P times E times the sine of theta. What theta maximizes sine of theta? Feel free to type it in the chat too. I've got the chat window open as of now.
It's 90 degrees.
90 degrees, exactly. So we know that when the angle is 90 degrees, it should have a maximum. So 90 degrees, which we'd also call pi over 2 if you're wanting to talk about radians. But either way, that's the important part. So when we're asked what is the maximum torque that can be applied to the water molecule, we can immediately say, well, that's when theta equals 90 degrees. And in that case, torque is equal to P times E times the sine of 90 degrees, which is equal to 6.1 times 10 to the negative 30 coulomb meters times 2.0 times 10 to the fifth newtons per coulomb. And notice the coulombs cancel out and you get newtons meters, which is exactly what you expect for torque. And then all of this is times the sine of 90 degrees, which of course is exactly 1. So in this case, we're going to get 12.2 times 10 to the negative 30th, or excuse me, times 10 to the negative 25th, which we can change to significant to scientific notation and get it, where it's only one decimal place or two decimal places, excuse me. But the number is 6.1 times 10 to the negative 30th times 2 times 10 to the fifth, and that gives me 1.22 times 10 to the negative 24th Newton meters, which we don't convert to joules. We don't call that joules. When we're dealing with torque, a Newton meter is just a Newton meter, but when we're dealing with energy, a Newton meter is a joule. So that's the maximum torque we can get. I'll call that T max, and I'll box it off with a distinct red box. So that's the answer to part A. But you might want to know exactly what that means. Well, the way the cross product is defined is that basically, if you have one vector, let's say this is vector P, and then you have another vector, say this is vector E, and they're tail to tail, then this angle is theta, so that torque is equal to P cross E, and so that its magnitude, torque, is equal to P times E times the sine of theta. So what is the point of maximum torque is when the electric field, let's say, points to the right, like so, and then the electric dipole will do like this. I'm going to use that and that. This guy up here is going to be my positive charge, and this guy down here is going to be my negative charge. But the key thing is you can now see that the P vector goes this way, and in fact, tail to tail, this angle is theta equals 90 degrees. So that's when the maximum torque is put on it. And that should make sense, right? When I multiply the Q times E, I get the electric field. And since the Q is just a scalar multiplied by the E, it should actually just point in the positive E direction. So this is literally showing that the little bit of force, which I'll draw with a black vector, the little bit of force that we're having is in fact right here this way for this one. That is F. Oops, it's trying to make pretty drawings out of my letters. That is F is equal to QE. Now on the other side, what you'll notice is the force is actually the opposite direction. And that's because the force is Q times E, but Q is a negative. So F is equal to negative Q times E because this charge down here is negative, and you see that they are in fact forces that are perpendicular to the lever arm, which is exactly what we expect for a Maxwell torque. Any questions on that part? All right, now it turns out that when you do the dot product, it's the same theta. So you still imagine P being tail to tail with E, and then in the dot product, the cosine of theta is what's used. So you're actually taking the cosine of 90 degrees for this part B. So in part B, they're asking specifically, what is U for the electric dipole of the water when the torque is at a maximum. So at T equals T max, theta equals 90 degrees, so that U, which equals negative P dot E, is, we're going to say U is equal to negative. Now I'm going to write my P, which again is 6.1 times 10 to the negative 30th Coulomb meters times E, which I left off that there, which is 2.0 times 10 to the fifth newtons per Coulomb. And now we're going to multiply that by the cosine of 90 degrees. And of course, the cosine of 90 degrees is 0. So we're actually going to get that the potential energy for this case is 0. So it turns out when the dipole is perpendicular to the electric field, it has no potential energy. Uh, Double checking, making sure. Yeah, cosine 90 is 0 degrees. Yep. And that's it. Another thing we could ask is in what position will the potential energy take on its greatest value? So you might say, under what conditions is the potential energy a max? So we've already found the answer that we wanted. So I'm going to go ahead and box that off. U at T max is equal to 0 joules. Remember, this time we got Newton meters again, but this time we're talking about an energy, so it's perfectly reasonable for us to say that is 0 joules. Now I'm going to say for what I call sort of part C, which I'll just call extra, you might want to say what orientation maximizes u. So our answer to that is cosine theta is a max at theta equals 0 degrees. It's a minima at theta equal 180, uh, but that really doesn't mean anything. It just means it literally is equally big, but in the opposite direction. So for this, in this case, what we'll find is that the angle should be 0, and you should have something like electric field pointing this way, and the positive and negative charges are lined up along that. When you're doing 0, for instance, the positive would be at that end, and the negative would be at this end. Oops, did I draw it a little better than that? Okay, it's just going to interpret that to be a square. Dang it, still did it. Okay, so that's good enough. We're going to call this one the negative charge. We're going to call this one the positive charge, and the P, therefore, points this way. And when that's the case, U is actually equal to 6.1 times 2.0, which is 1.22 times 10 to the same number we got before, negative 24, but this time it's not torque, it's actually in joules. Any questions on that? Okay, so
Nope.
that basically closes off everything from chapter 21. Chapter 22 is innately different, and it's supposed to be really quick. It's about Gauss's law. So let me start off by saying,
Sorry, Professor, could I
yes,
just
sir.
jump in with
Yeah,
a
no problem.
question on the very last thing? Is that just a conservation of energy thing going on there?
Yes, yeah, it's for us to use, for instance, conservation of energy, like you did in chapter, I think it was 7 and 8 of last semester, if you took the same book, anyways.
Yeah, it's again like everything. It's been a minute.
Yeah.
So is torque related then to kinetic energy? Is that how we
Oh, okay.
understand it?
So torque is really just the ability to make something rotate or accelerate in a circular direction. So it's, what you use to loosen a bolt or to tighten a bolt or technically a nut. But you could also loosen a bolt and a nut too. So anyways, that's what the torque is used for. It's just used for rotating, whereas it's the rotational analog to force, say.
Okay.
Does
Thank
that
you.
make sense?
Yep. Thank
All
you.
right. So with chapter 22, we're calling this Gauss's law. Now, a friend of mine, a very wise friend of mine, his name was Casey. He shared an office with me at Chapel Hill, and he'd say, he'd get on his students. He says, "It's Gauss's law, not Gauss's helpful hint that sometimes works." So, I will reiterate that Gauss's law is in fact a law, but at this level of course, in at this point in your life, you're going to use Gauss's law in a very, very weird way. And using it that very, very weird way does actually require certain criteria, or you can't use it. So I understood why students sort of think that Gauss's law is only sometimes valid. Gauss's law is always valid. We just can't use it the way we want to in some cases. So what Gauss's law is about is something we call electric flux. And electric flux, we give the Greek symbol capital Phi. And what it is you sort of imagine how many uh, how many electric field arrows can go through a hole or a window or something like that. So if you look, for instance, at a three-dimensional structure, let's say we have a window. Actually, let me get off of that drawing. Okay. If we had, for instance, a window that looked like this, I'm going to go back 2 spaces there. This would be the top of the window. And then we'd come down like this. and do like that. And then we're going to come down here. That thinks that looks pretty good. Come down here. And then this window goes like this. Now, if you imagine the electric field vectors as if they're these purple lines here, there'd be one here, there'd be one here, there'd be one here, and then maybe there'd be another one here, another one here, and another one here, and then maybe there'd be another one here, another one here, and another one here. You can sort of see that all the electric field lines are going to get through there, right? You could even imagine it, and that's why I did it sort of three-dimensional, like it's a path. If you imagine this path as going really, really, really far back, it would make a better point, and the point that I'm trying to make is that basically if you have a vector that isn't exactly parallel to this path, then it's going to encounter some problems when that vector tries to go through here, because if this tunnel here is long enough, then any component of the electric field that's not exactly parallel to the path is probably going to be hit, or going to hit the walls and in some sense be absorbed. So if you think of flux as a count of the total number of lines that could make it through a tube, then you'd be on the right path of what we're looking for. So yes, these vectors that I drew would be perfect because they're all exactly parallel to the tube that I made. But in reality, it's much more likely that your vector is going to look like this, and that it has these components. The blue component being a component parallel to the face of the hole, and the purple one being perpendicular to the face of the hole, are therefore parallel to the tunnel. If you just want to count those, then what you could do is you take the electric field E. I'm going to go back to black now. You take the electric field and you make a dot product of it with a area vector, and that would give you the ability to pick off the component of E that is actually parallel to the area vector. So what we're going to do is imagine that this window is really big, but because the electric field could vary all over the face, maybe we need to focus on an itty bitty section like this of the window. That would be a DA. And we then need a vector to represent its orientation. Since it's sort of like the screen of my calculator. When I lay my desk on my my calculator on my desk, the screen of my calculator is exactly parallel to my desktop. And if I try to represent that orientation by any vector that I could fit in the calculator screen, I get no really good reasons for it. I'd say perfectly to the right, and they'd say, okay, well, why not perfectly to the upward direction? Or why not perfectly to the leftward direction? Or why not perfectly to the downward direction? And I'd be like, yeah, there's really no good reason. And then you say, well, 45 degrees. Well, there's a whole other set of reasons there. So there's really no good vector direction within the plane of the screen that is a good representative of it, because everyone has an equal complaint to or equal reason to the other ones. But if you say maybe we take a vector that's perpendicular to the surface, then what we'd have is this option or this option, and that's all. So that's what we've done. We've chosen to represent a rectangular area, or any area for that matter, by a vector that's perpendicular to that surface. And the ambiguity, of course, is whether it's this one or whether it's this one pointing down. And what we do is, it turns out the flux through an open window doesn't have any physical meaning that helps us with anything. But if you think of the flux through a closed surface, in other words, like through a cylinder or through a sphere where you literally have to go through the walls of a container to go from outside to in or from inside to out. Whereas, like a toilet paper roll, that doesn't have the end cap, so you could literally go inside the tube and be inside and then slip right out the outside, and now you're outside, but you didn't cross through any surface. So it turns out if you actually limit yourself to the flux through a closed surface, then you can unambiguously say that the vector is going to point outward. So now instead of just imagining a single rectangle like the screen is, what you're going to imagine is this single rectangle is a small part of a giant, let's say, spherical surface. We just happen to be so close to it and the radius so big that over this, roughly 1.5 inches by 3 inches, over that area, it's essentially flat. And since the sphere is all over there, then this is pointing outward. This is not the convention. This is the convention. So when we have a closed surface, we define the vector to not only be perpendicular to the surface, but also to be pointing as if it's pointing out of any closed surface. If it's a non-closed surface, you can choose either one you want, out or in, and you're equally valid in both. So by doing this, taking E dot A, we do get a measure of what I called flux. But it turns out when you go to handle electric fields that rapidly change around surfaces, that could, of course, rapidly change as well, then you might have to drill down a little deeper and figure out a way to compute the total number of field lines going through the surface. And to do that, you might be compelled to make a little rectangular opening on the surface of the sphere. And that little rectangular opening, if you find that the electric field still varies on that, anywhere on that little window, then you cut the window even smaller until you find no variation. But the main thing is you try to find an area where the variation between the electric field at one corner doesn't change significantly from any other point in it. Okay, so if you only need, for instance, 3 decimal places, you might be able to use a bigger window than if you needed 5 decimal places. But now we have that, and we have this little vector whose length is going to represent the actual area itself. Therefore, we're going to call that quantity dA. So by making it really, really small, we call it a differential area element, dA. And the direction, of course, if it's on the surface of a closed surface, then it's clear what the inside and what the outside is. So you're going to assume that the vector points as if it points from the center out. So, and I've got it drawn correctly in this case. Now, in doing that, because you have to actually make the windows into small little portions all over the surface, you then have to add all the results up, and adding up so many results is really what we call integration. So we call the electric flux the integral of E dot dA. So notice it sort of looks like the formula we had for work, which was F dot dL, but it's innately different because F dot dL was what we called a path integral, where you were integrating a function along some kind of path in an arbitrary space. In this case, you're actually calculating the number of lines penetrating through a closed surface. And you're wanting to count, for instance, the ones that are exactly perpendicular to the surface. You're sort of wanting to say those are really important, whereas the ones that have an angle with respect to it are less important as the angle gets bigger and bigger than zero. Okay? So that's the electric flux. It's not something that has much use other than in Gauss's law and the early advents or the early discoveries of trying to figure out electricity and magnetism. They found a lot of different ways you could make use of electric flux, magnetic flux, all this stuff. But it turns out at the end we get Gauss's law, and it's a law about the electric flux through a closed surface. So we're going to actually take this integral and we're going to draw a circle on it. And that doesn't mean the math is any different. That circle just says, hey, this formula that has this pretty integral in it is technically a surface integral, and the circle on it means that it can only be applied truthfully or correctly if the surface you're analyzing is a closed surface, meaning it has a clear inside and outside. So that's what we need to make sense of Gauss's law. It's not going to be trivial to show it to you, but I'm going to show
So
you. Go ahead.
I have a question. So when you're saying that it only applies to certain scenarios as far as Gauss's law is you're referring to the instance that has to be a closed surface?
Exactly. It always applies. Gauss's law gives you
Right.
a formula that's always true. But when we go to try to do the weird thing we do with it, we have to have very special conditions of symmetry in place. So,
Right.
yeah,
Okay. And then remind me again real quick. E represents
electric field.
the electric field. Okay.
Hmm.
All right.
Yep. Glad you asked me because that's definitely something that's sort of helpful. And remember, it's going to be like in newtons per coulomb, and later we'll have it in newtons per meter, I mean volts per meter, but that works well. And this, remember, the A is an area. So what we're imagining here is the actual vector has a length that's equal to the area of the little rectangle that it's on. And it's not always going to be a rectangle. You could use different coordinate systems and it'd be different shapes, but the main thing is that's what we're going for. So what I want to do is show you how to do the calculation of one side of Gauss's law. And what we're going to do is we're going to imagine that this is the x-axis, this is the y-axis, and this is the z-axis. And then dead center, I'm going to put a point charge q, specifically positive q for reasons that don't really matter too much, but just maybe make it concrete. So now what I'm going to do is try to imagine exactly what a surface would look like in this space such that the electric field strength is a constant all over it. So remember what we found out from Coulomb's law. From Coulomb's law, we discovered that the electric field has a magnitude equal to Q over 4 pi epsilon naught r squared, where r is the distance away from Q that you're measuring the electric field. So that's the formula we have for an electric field due to this charge Q. Can you imagine a surface that would have the electric field's strength constant all over the surface?
Circle.
A circle, that would be the two-dimensional part, and the
Oh, a
three-dimensional part.
sphere.
Exactly. There you go. So what we're going to do now is I'm going to draw a sphere around it, and we're going to actually call that sphere a Gaussian surface. It's a whole language built into it and everything. So I'm trying to draw a Gaussian surface, and this is the key point: is you want the Gauss. Oops, I didn't have it on correct draw. You want the Gaussian surface to be able to be having a constant electric field everywhere on it. And of course, the way we do that with this point charge is we have to have a spherical surface. Whereas the other symmetries that work that are nice are cylindrical symmetry, but it has to be an infinitely long cylinder, like the first one we did last class, or it has to be an infinitely large plane like the thing we did last in last class. So now that I've got this sphere, we can imagine that it has a very specific radius r, and we might even imagine that the little differential area element on this surface right there is in fact that little differential area dA, and the vector pointing out of it is dA equals, in this case, I'm going to say it's just some magnitude dA, and it's going to point radially outward, and there's a coordinate direction, there's a unit vector associated with that, and it's called the radial vector r hat. So just like I, J, and K, only this one always points from the origin outward. Okay, so no matter where you are in space, if you want to find the r hat vector, you put a dot down at the place you want to know where that r vector is, and then you draw a line from the origin to that point in space, and then you extend that line exactly 1 unit longer, and that is a vector that represents r hat. Okay, so now we can try to calculate the what would we call the left-hand side of Gauss's law. And the left-hand side of Gauss's law is the closed integral of E dot dA. And we're going to make a hypothesis because what we know about symmetries and the electric field strength is that the electric field from a point charge should only point radially outward. So I'm going to say it's a vector, and I'm going to say it's parallel to the r vector, and I'm going to say it only depends on the distance you are away from the center, so it's only a function of r, and we're going to say that vector is E of r, a scalar magnitude, times r hat. That's our hypothesis. Okay, so I plug that into the integral. I get E of r hat. And actually, that last vector symbol that I drew before the r one, that wasn't supposed to be there. So it's going to be E of r hat. And then we're going to dot that with the dA vector, which is dA r hat. One of the key things about the dot product and the cross product for that matter is when you have a scalar in between the two vectors, you can just pull that scalar out in front. It's linear. It's a linear operator is what we call it. So we can actually take this integral and just call it E of r times dA times r hat dot r hat. Now we know the formula for dot products is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Well, if we do that in this case, unit vectors have a magnitude of 1, so it's 1 for that one, it's 1 for the other one, and these are actually parallel, so the angle between them is 0 degrees, so cosine of 0 is 1, so you just get a 1 for that, okay? Not only that, since we're doing this integral on the surface, that's why we call it a surface integral. It's a whole different type of math that you only would learn in your Calc 3 course if you're lucky. And like I said, I've been to 3 places and none of them were able to get to surface integrals or line integrals within the 3 semesters of calculus. So I don't think it's going to happen too often, but you are expected to learn it. So here it is. What you're now going to do is you pull this
Isn't,
E.
well,
Go
hold on.
ahead.
Isn't line integral the same as linear algebra or something different?
You could, yeah, you could cover those in linear algebra. Uh, yeah, you could definitely cover those in linear algebra. You can talk about algebras with specific types of metrics and distances and stuff like that, and sometimes those revolve around path integrals and stuff like that.
Okay.
So, yep.
Sure.
But they usually don't have them. They'll sometimes have like a derivative space, but they could, in principle, even cover Hilbert space, which is infinite dimensional and real and imaginary. So all sorts of crazy stuff can come in. Now that we have that, though, remember I did figure out that the r hat dot r hat was 1, so I don't have to have that anymore. Since we were conducting the integral on the surface that was a sphere, and the radius of the sphere was r, and the magnitude only depended on r, that meant E of r had to be a constant, so I could pull that out in front of the integral. So I just get the integral, or excuse me, E of r times the integral of the differential area element, which over a whole sphere becomes the formula for the surface area of a sphere, which is 4 pi r squared. So the result for the left-hand side of Gauss's law is 4 pi r squared times E of r. Okay. The right hand side, on the other hand, this is the part that usually requires can require more work. The left hand side is always going to be like some area times a electric field magnitude. It's always going to be that if you're using Gauss's law to extract the electric field out of the integrand of Gauss's law, that's the weird thing we're doing with it. As long as you're using Gauss's law that way, it's only going to work if you have spherical symmetry infinitely long cylindrical symmetry, or infinite planar symmetry. So an infinitely large plane or a plane that you're really close to. But the right-hand side is supposed to just be the enclosed charge. Remember, I told you had to integrate it over a closed surface? Well, all the charge inside of that closed surface is charge enclosed. So any charge that's inside there has to be added with all the other charges inside there. And then you got to divide that by the epsilon zero that you recognize from Coulomb's law. That's the same 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. In this case, we know the total charge enclosed is that plus Q. So I'm just going to put a Q there. And the epsilon zero can't change. That's just going to be epsilon zero. So that's the right hand side. Now you can set left hand side equal to right hand side. And what you'll get is basically Coulomb's law. We're going to say 4 pi r squared E of r is equal to Q over epsilon naught. Therefore, E of r, which is what we're really trying to determine, because remember we made a hypothesis that E of r multiplied by r hat is the actual electric field. This is us solving for that E of r. So what we're going to do now is we're going to take that E of r and solve, and what we get is Q over 4 pi epsilon naught r squared, and then by our original hypothesis, that vector should point in the r hat direction. So that's it. We've now managed to actually solve for the electric field. And actually, since I wrote E of r there, that's all I can write. Now I can say that now I can say that E, the vector, is equal to E of r hat, which gives us Q over 4 pi epsilon naught r squared r hat, like that. And that is the formula you get when you apply Gauss's law to a point charge at the origin. But the cool thing is it doesn't have to be a point charge at the origin. It can be a spherical charge at the origin. And you could even, for instance, use a spherical charge that's not uniformly distributed. For instance, you could have a spherical charge whose charge density is some constant times r, or whose charge density is some constant times r squared. All sorts of cool stuff. And we're going to do some examples like that, but that's the intro to Gauss's law. Now I am in a position, now that you have some understanding of what I just showed you, I can state what Gauss's law is in integral form. So Gauss's law, integral form, says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And that sort of comes with the caveat that Q enclosed could be equal to the integral of lambda dL, or the integral of sigma dA, or the integral of rho dV. Just like we were using before, we can still use charge distributions. If they say it's uniformly distributed over a sphere, then basically you're treating it as if rho is a constant and you're doing that bottom integral. If you're saying that the charge is distributed uniformly over a flat surface, then you're using the sigma in the second form, and you're saying that that sigma is a constant, so that any square inch you pull off will have a certain amount of charge. And if you next pull off 4 square inches, you're going to have 4 times as much charge. And if you next pull off half a square inch, you're going to have half as much charge, so on and so forth. That's what the uniform charge means. And if it's a line of charge, that means basically that the lambda is a constant. Okay? So we only got a couple of minutes left in the class, so let me show you applications of Gauss's law. We just did one for a very simple sphere. What I want to do now is one for, and I'll put some more up videos before our next meeting probably. But anyways, keep an eye on that, but I'm going to go ahead and do another one now. Let's look, for instance, at that really bad problem, that the very first one we did last class. We're going to solve that now using Gauss's law, and I think you'll be surprised at how much easier it is. So let me draw my coordinate system real quick. Remember, we're treating this as if it's a infinitely long line of charge, and that infinitely long line of charge has charge distributed along it uniformly, so that every millimeter has the same amount of charge as any other millimeter thick slice. What I'm also going to do is show you the wire, and for some reason it tried to make it right where I didn't want it, so I'm going to undo that and draw it further over here. And then I'm going to make another one, and I'm drawing this far away just because I don't have any choice. This stupid thing tries to make it the same thing. Now I can pull this one over here. Okay, so we're imagining this going on forever. This axis will be my x-axis, this axis will be my y-axis, this axis will be my z-axis, and just like we did before, we're thinking of this as if it is lambda equals a constant distributed charge. And we're going to try to calculate what the electric field is at a distance r from the center. So what I have to do is I have to use Gauss's law, and Gauss's law says the closed, oh, evidently my program's doing aggravating things. So what represents Gauss's law is the closed integral of E dot dA is equal to Q enclosed over epsilon naught. That's Gauss's law. What we do is we have to find an electric field because we're trying to extract this electric field out of this integral. That's the weird thing we're doing with Gauss's law, and that can only be done if it has one of those symmetries. So what we got to do is we first need to look at the charge distribution and make a hypothesis about the electric field. So I think the electric field due to this thing should point always sort of radially out, but not like radial out from the spherical coordinate standpoint, but radially out from like a cylindrical standpoint. So, for instance, the r vector, the vector that points in the direction of the electric field, that is going to have an x component and a y component maybe, but it's never going to have a z component because it's going to point all the way back. Like if you imagine walking along the tip of the arrow all the way to the tail of the arrow, if you continued on that walk for however long you needed to, you would eventually run right smack into the z-axis. If you happen to be at z equals 0, you'd run right smack into the origin. But that's the key aspect of this. So there is a coordinate for that. It's the cylindrical r hat coordinate. So I'm just going to use it r hat, and I'll just tell you it's the cylindrical. So my hypothesis is that the electric field about this wire is a function of that r that lies in the y in the xy plane. In other words, the distance horizontally from any point on the wire to the point out r away from it. That's what the magnitude is going to depend on, only on that variable r, and it's going to point radially outward. But I want to remind everybody, this is the cylindrical coordinates, radial. And again, what that means is it's r hat equals something times I hat plus something times j hat. I can actually give you what those are. It doesn't really matter too much. It's cosine theta, I hat plus sine theta, j hat. but it's not important that you know them. So anyways, that's what we're using as our hypothesis. Now that we have that hypothesis, we're going to try to guess of a Gaussian surface. So earlier, for instance, Joshua told me that what he knew about the Coulomb's formula, E equals Q over 4 pi epsilon naught R squared, was that a surface on which the electric field strength would be a constant would be a circle, and then he realized it's 3 dimensions. He said a sphere. What surface, on what kind of surface will the electric field strength be constant for this particular orientation or for this particular charge distribution? Anybody?
Um, well, wouldn't it be well, it's a circle, but isn't it projected along the z-axis? So wouldn't it be a
Exactly.
cylinder?
Exactly. It's a cylinder. So yeah, I'm going to draw what we call a Gaussian surface. And this Gaussian surface is a cylinder with tops and bottoms, don't forget. So it's going to go right like this down to here. And this is just the Gaussian surface. It doesn't have to enclose the entire wire because the wire is infinitely long. But more specifically, I'm choosing a cylinder whose length is L and whose radius is R, which happens to be the distance away that we wish to know the electric field. Okay, so we've got a charge per unit length, lambda, and we've got a cylinder of radius R with tops and bottoms. You can imagine, though you might not have thought of it, that the differential area element vector for this guy has got to be pointing straight up. That's dA for the top is equal to dA k hat. For down here at the bottom, it's going to be dA bottom is equal to dA, or excuse me, equal to negative dA k hat. In other words, it'll be exactly the same form as the top one, but it has to point down, so it'll be a negative. That's not really easy to see from this, but I guess we should move on. And then out here, it'll be a little rectangle on the cylinder, and that would be dA, what I call soup label, is equal to dA, in this case, R hat, and that R hat again is cylindrical. Okay. Now that we have that, we can go ahead and work the left-hand side. So let me show you how to work the left-hand side. And this is the way you implement it. You work out the left-hand side, you work out the right-hand side, you set them equal to each other, and then you solve for the electric field strength. So the left-hand side is the closed integral of E dot dA. So that's going to be the integral of our hypothesis, which is E of R hat, cylindrical again, dotted with, in this case, it'd be the top. So I'm going to say dA top k hat, which actually I could have subscripted all those. I just did the leading one. So that's one part. Plus I got to go the integral over the soup label, E of R hat, cylinder again, dotted with dA soup label times R hat, cylinder again. And then plus the integral of the bottom, E of R hat, dotted with negative dA k hat, and this for the bottom as well. So the main thing that you're going to see here is, remember I told you the dot product's a linear operator, so I can pull that dA out in front of the dot product. I can pull it over to here. So I'm going to get R hat dot K hat. But like I said, R hat has no K hat component. So when you dot product them, you're going to get 0. So this one gives you 0 by the dot product. The same thing happens with the bottom one. That gives you 0 by the dot product. Okay, so those two cancel each other out. However, on the soup label, which is the literally the soup label of that can, the E of R is a constant, and you get basically you get E of R that you can pull out in front is equal to the integral of dA soup label times R hat cylinder dot R hat cylinder, which is just 1. So you end up getting E of R times 2 pi R L. Because if you cut the soup label, it would be L units tall and 2 pi R units wide. So that's exactly the left-hand side. Now I can say right-hand side. We're almost finished. Sorry, we are 2 minutes over already. The right-hand
You're good.
side, thanks, is Q enclosed over epsilon naught. And that Q enclosed, since we chose lambda to be the charge per unit length, all we got to do is multiply the charge per unit length times the length, and that'll tell us how much charge is enclosed. So I'm going to write up here lambda times L for the charge enclosed, and we get lambda times L over epsilon naught. Now I can set left-hand side equal to right-hand side. And when we do that, I get E of R times 2 pi R L is equal to lambda L over epsilon naught. You can immediately see that the L's cancel out. And lo and behold, we're going to get a really nice answer. Specifically, we're going to get E of R is equal to lambda over 2 pi epsilon naught R. And check this out. This was what we learned last class. Lambda is equal lambda over 2 pi epsilon naught R. So you can see we got exactly the
Neat.
same result, a lot easier. And of course, now we go back to our hypothesis, and that tells us that the electric field as a vector is lambda over 2 pi epsilon naught R, and R hat cylindrical. So you can see when I covered it last time, we didn't know about anything about cylindrical coordinates, so I just said it had to point radially outward, which is the J direction. And that's exactly right in this drawing. The J direction is exactly the result. Well, that's also exactly the result for this drawing. It's just now I've told you about this R vector, so this R hat vector would point literally right there at that point. But if you're over here on this part, it would point this way. And if you're back here on this part, it's going to point that way. If you're over here on this point, it's going to point that way. And notice it never has a upward or downward component. It's always in the XY plane, at least in terms of directions. So that was hopefully a straightforward enough calculation of Gauss's law. We've now seen a sphere and we've seen a cylinder. We should be able to finish up the rest of it next time and probably start into chapter 23. You guys, of course, are free to go. You're also able to stay around if you have any questions for me, and I can work on that, or you can go ahead and split.
Thank you.
No problem,
I
Jeff.
just do have a question on the left-hand side portion,
Okay,
on the first integral.
gotcha.
So
This
R hat
problem.
cylinder,
Mm-hmm.
um, that is, so is that equal to, why is that, what is
This
that equal to?
Okay, so remember R hat cylinder is technically, I'm going to turn it to another page.
Yeah, you're good.
R hat cylinder is technically just cosine theta I hat plus sine theta
Oh,
J hat. So if you actually take a dot product of K hat with R cylindrical hat, then what you get is cosine theta I hat plus sine theta J hat dotted with just K hat. And of course, you got to use the distributive property, but you're going to get cosine theta times I hat dot K hat, which remember is 1 times 1 times the cosine of 90 degrees.
okay.
And then the other one's going to be the same thing except sine theta J hat dot K hat. So this time you got a sine and a J, but again, that is 1 times 1
Times
times
one.
cosine 90. The cool thing is you don't have to think about this stuff at all. I'm showing you those gory details, but the left-hand side always is going to become electric field times some area. That's it.
Okay.
Might have a
So
number
you
in
just
front of
that
it.
was the derivation.
Yeah, I'm showing you all the gory details, and when you actually practice this, you're probably going to start at this line. Hopefully, you'll show me that you know that it's broken into three different parts, and then you'll write this answer. So
Okay.
this is just convincing me that you know it's three parts. This is the definition, and this is the next line.
Okay. All right. And
Look at the other one
then
too, the spherical one. Look what we did with the left-hand side there. It was the r hat dot r hat. That was 1 cosine of
right.
0. But again, the electric field just popped out in front, and we had the
Hmm.
integral of dA. So really all you had to know was it's going to be the electric field times the integral of the part of the surface that was relevant. In the case of the sphere, that was the whole spherical surface. But in the
Right.
case of the cylinder, the electric fields were perpendicular. Ooh, I shouldn't have wrote it that way. The electric fields were actually perpendicular to the dAs up there and down here, but they were exactly parallel for these.
Okay.
Does that make sense?
Yeah, I just got to digest it.
Yeah, that's all it is. And like I said, it really it's this is supposed to be so easily understood that they literally do the same thing in the 202 class, only they don't show an integral. They just say delta A.
Okay.
So that's what they're wanting you to do is they're really wanting you to sort of black box it. But you guys are smart enough. Y'all don't have to completely black box it because you've had some calculus. So I just show you a little bit more.
Yeah, I wonder what physics would be like without calculus, like from a 202 perspective, but I just,
Yeah,
no,
it was a
yeah.
lot harder. I took it first because that was the only physics they offered at the community college that I attended.
You think it's
So that,
harder?
oh yeah, yeah, I thought that. I mean, it was easier in the sense that, in retrospect, I could go back and solve those problems all day a lot faster than you can with physics 242 or 241. But it was
Right.
harder in the sense that, I had a real hard time figuring out how to do stuff in that class. Whereas the first time I took 241, that was trivial. I mean, it was like almost obvious. I couldn't believe that students were having a hard time with it. Uh, but that's partly
You're
because
blessed, man.
201 is so
Hey.
easy. Yeah. I mean, because you had 201 and 202 already, you're pretty darn prepared for physics at that point.
Yeah, I guess.
Uh,
Yeah. Okay.
all right.
And then I guess just to clarify, yeah, I saw your email. For us online, we have to see it or take it proctored. And when
Yeah.
you mean by proctored, you mean can we schedule a time in the like a testing
Yeah. That you use
facility
the testing center, any testing center on any of our
or
campuses, or me.
in front of you?
Yeah. That's why I gave you all those times. And you have
Right.
the option of going Monday as opposed to one day this week.
Okay. And then your class times are, is it Monday, Wednesday?
Yeah. That's the ones I'm on campus face to face.
Okay. Okay. All
How
right.
about you, Matt?
I'll
You got any questions? Oh, go ahead.
well,
Go ahead, Josh. I just
No,
wanted to
I
like
make
was
sure
just
Josh,
because
gonna
I need
say
to spend some time digesting this material, but yeah, no questions now. Thanks.
yeah, no problem. Feel
yeah.
free if you have questions, go ahead. But I just want to make sure you knew that I knew you were here still. Go ahead, Josh. I'm sorry.
No, I was just gonna say I'll give you a heads up as to what I'm planning on in terms of when I'm taking the test.
That's
So
cool. Just don't forget to take it. That's the main thing. Is I hate that when my students just forget
well,
and don't take it or whatever.
I won't forget.
Okay.
But all right. Well, you have a good night. Thank you.
You too, and don't forget it's only up to 20. You don't have to do this stuff on that one.
Right. Yes, I'm aware of that.
All right.
All
See you,
right.
Josh.
All right. See you.
Take care.
Yeah, nothing for me, Professor. See you next time.
Do you don't need any more explanation on this crazy stuff that I just showed you? It's perfectly fine, and I don't have to record it. I can kill it if it wants, but trust me, if
Nah,
you're confused, you're supposed to be.
yeah, I'm a little confused. I'm going to go back and try to slowly work it, um, and then I'll raise questions if I have them, if and when.
That's cool. And look at the examples in the book. Your authors does a pretty good job explaining it. He don't do a lot of the details I do, which in some ways that's infinitely helpful to you. So if you just memorize that way, it's going to work every time. Uh, but if you come back, 3 weeks from now and you're like, I really don't understand how he got that, then mine might become more helpful to you. Sometimes mine can be just as much as a blood clot to your learning as as the other way. So, don't assume it's just my way or the highway. If you can do the left-hand side and the right-hand side and set them equal, you're gonna do fine. And it really is something that we let non-calculus students do. So you,
Okay.
you can get it. I'm confident.
All right. Got it.
All
All
right.
right. Well, I'm gonna run. I'll see you next
All
time.
right.
Thanks a
Take
lot.
care, Matt. Thanks.
Yeah. Bye.
Okay, so that looks like we did everything pretty good there. I don't see any big errors. Uh, yeah, I think that explanation did okay with the tube. So that'll be it. I'm going to stop sharing and now I'll say bye bye.